Excellent. Okay, thank you. So it's very nice to welcome Zoe Todd from the University of Washington in Seattle. And Zoe has been there for about a year. She's a Carl Sagan Fellow. Zoe, please correct me. Is that the right name of the fellowship?
Yeah.
Yeah, and this is a very nice fellowship actually. So to put you a bit into context, Zoe is an independent postdoctoral fellow. So she does her own work. She wrote a nice proposal, got funding for it. I think she still has something like 2 years to continue with the project. And she's working in the group of Professor David Kapling. But before that, she was at Harvard. She did her PhD in the group of Dimitar Saselov. It is really important to mention that this was very interdisciplinary work, because it was really at the interface of planetary sciences and chemistry, with the focus on prebiotic chemistry and the origins of life, and in particular the role of UV light in abiogenesis, so the emergence of first biomolecules on Earth, and possibly also in some extraterrestrial conditions. And what is even more important here is that her view on it, and also the research which she does, offers a very fresh set of ideas about how these molecules could have emerged under the influence of UV light. Before that, the ideas were much more simplistic. I had the pleasure of collaborating with Zoe in several cases, since I'm a theoretician and what she does is more experiments. So it's always very complementary to do theoretical and experimental work. And what else I can say? I think I'm just wasting your time, and it's really, it will be really nice to listen to what you have to say, Zoe, today. So take it away. The stage is yours.
All right. Well, thank you so much, Rafal, for the kind introduction. Thank you all for inviting me, Tomas for organizing, and everyone else for inviting me and having me here to speak. I'm very excited about this. All right, so I will share my screen now. And at any point, if you have questions during my talk, please feel free to interrupt me. I'm happy to have a discussion during stop questions. All right. Okay, can everybody see that? Yes. Okay, awesome. So today I thought I would talk about the topic, are we alone? Through a tour of our universe and its implications for other life. And I put down here my email, so if anybody would like to get in contact with me afterwards, please feel free to. I'd be happy to continue the discussions. All right, so let's start with where we are. Sometimes when I start this talk, I'm able to pull up a Google map with a precise building and be like, you are here. I figured that's a little bit more difficult today, considering I'm half the world away from you guys. But maybe some of us are just all over the place. So roughly speaking, you are here. And as I continue in the next 15 minutes or so, you might realize how much we all could feasibly be overlapping in the same exact place for all it matters in our space in the universe here on Earth. So you are here somewhere on the Earth. I'm over here. You guys might be over there in some location. I should test myself and see if I could point out Poland on the continental Europe without boundaries. It'd be interesting. Okay. So now let's zoom out a little bit further from Earth. So Earth is the third planet around our sun. Our star right here is called the sun. So we have Mercury, Venus, Earth. Look, there we are with our moon circling us and Mars there. So the Earth is located 1 astronomical unit, or 1 AU, away from the sun. So as we go outward on this journey through our universe, I'm going to try to keep mentioning distance scales and sizes, but feel free to let me know if you have questions on that. You'll notice that the scales will get vastly different as we continue throughout the time. All right, so now zooming out a little bit further. So this red line here was Mars, and then this red line right here is still Mars, but now we're looking at our outer solar system. So we have the asteroid belt here, and then Jupiter, Saturn, Uranus, Neptune, and then here's Pluto, kind of not a planet anymore, dwarf planet. So you can see that our inner solar system and where the Earth is around our star are much closer contained and on smaller distance scales than our entire solar system. I think Neptune and Pluto are at about 40 AU, so they're about 40 times further from our star than the Earth is. So already our distance scales get pretty big on this scale. All right, now what happens if we continue to zoom out beyond our solar system? So here we are around the sun, and then if we look at our nearest stellar neighbors, these are some of the stars that live closest to us. So I personally come from an astronomy training in my undergrad, but I will freely admit that I do not know many star names, and I'm not the best amateur astronomer out there. If anybody is into amateur astronomy, I'm sure you know much more than I do. But now if we go to a slightly nicer picture of our nearest stellar neighborhood, so here we are, the sun at the center with our nice yellow star. And then you'll notice that these stars, in addition to having their names, have their sizes and colors indicated as well. So our sun is yellow. It's kind of middle of the size range in terms of what stars typically can be. And then you'll notice you see a lot of these red M-dwarf stars in our nearest stellar neighborhood. They are the most populous stars in the universe and in our galaxy and in our neighborhood. And we get some bigger stars, some supergiants. So for instance, here's like Sirius A and Sirius B. They're a binary star system, so they orbit each other. And I believe this one, Sirius A, is actually in its supergiant phase. So it's currently dying, and it goes through these accelerated phases where they get very big and very bright and luminous. So important thing when we look at this stellar neighborhood is to realize that the most common stars out there are these red small M-dwarf stars. And these stars actually will also live much longer than stars like our sun, which has a lifetime of about 10 billion years too. All right, so here's the sun, here's our nearest stellar neighborhood, but where are these stars? Where do we live in a bigger context? So we actually live in the Milky Way galaxy, and we live in one of the spiral arms of this galaxy. So the Milky Way is this big, beautiful spiral galaxy. I'll show you a picture of what we think it looks like. And then you'll notice our sun is somewhere in here. So it's not in one of these really dense arms. It's not in the center of the galaxy, but we are located in one of these more dense arms of the Milky Way galaxy here. All right, so zooming out a little bit further, and you can see things like the Orion Nebula. So Orion is one of the few constellations that I can recognize and point out in the sky. So if you look up and you see Orion, around one of those stars is a nebula that we frequently talk about. And we are in something called, let's see, the Dixon spur here. So the different arms have different names according to constellations. Things like that. All right. So now moving out even further in the Milky Way galaxy beyond our spiral arm to see the total view of our galaxy. So this is what we think the Milky Way looks like. We can kind of guess this from looking at other spiral galaxies and also looking at the stars, but it's a little difficult to actually see what something looks like when you live inside of it. So here's where we are in our solar system. Here's the local arm, the Orion arm, the various arms around here. You'll notice that the galaxy has a vastly different morphology when you go to the center. So in the center is something called the bulge of the galaxy, where you have a much higher stellar density, and you have a lot more stars, a lot more light, a lot more mass located in here. So if you lived much closer to the center of the galaxy, if, for example, our solar system was here, the night sky would look very different. It would be much brighter. You would see a lot more stars. So that would be kind of fun, but kind of terrifying too, perhaps at the same time. And then our distance scale here is something like in, I believe this is light years. So from the center to the edge, it's about 40,000 light years. All right, so now that was our Milky Way galaxy, which is where our star and our solar system live. What about other galaxies? So the Andromeda Galaxy is our next nearest large galactic neighbor. So if you go out beyond the edges of our galaxy, look out in the night sky, you can see Andromeda. I think you can only see this from the southern hemisphere. So that's something that I think it would be awesome to see one day. Yes, and please feel free to put questions in the chat. I will hopefully be able to see that. And if I don't see that, someone, please feel free to interrupt me. Okay.
I have a question.
Yes.
Is it harder to see on the other side of our galaxy and map objects on the other side because we have a center of our galaxy on the way?
Yes. So we actually can't see through to the center of the galaxy to the other side. So there's something really interesting called like the Supernova Paradox, which based on the number of stars in our galaxy, you would expect to see a visible supernova in the sky like once every 100 years. The last one that we had was in like the 1600s. It was Kepler supernova. So one of the possible solutions to the supernova problem is maybe they're all happening on the other side of the galaxy and we just can't see them. So yes, that's something to definitely consider, is how biased our observations are because of our location in our galaxy. Does that answer your question?
Yes, thank you very much. I also recently heard about Crab Nebula that was dated to some ancient times, and in some records, people actually found some notes about that.
Yes. Yeah, it's like these supernova, when they happen, I think they would outshine the moon typically in the night sky, and you could see them during the day even. So it's really phenomenal when they have happened in the past, and many people keep records of these, and that's how we have some idea that they occurred. But I'm kind of like crossing my fingers for one to happen in my lifetime, because that would be really cool to see. You just don't want it to be too close to you, because then it might be not great for us as life on Earth. Yeah. Okay. Any other questions at this point? Okay, awesome. Please feel free to interrupt at any point or type it into the chat. Okay, so this is the Andromeda Galaxy. It's also a spiral galaxy like our Milky Way. It's our closest large galactic neighbor, but it's not actually the closest galaxy to us. There are much smaller dwarf galaxies orbiting closer to us, which I'll show you in the next slide. But Andromeda and the Milky Way, you may have heard this, are actually on a collision course. So because they're both so massive and they're both fairly close together, they are interacting gravitationally already and will be coming together and merging. I think the time scale is something like 5 billion years from now when they start really interacting. So you might look at this picture and look at the picture of the Milky Way and say, those are so dense. Like when they collide, what happens? Does everything just smack together? And actually, that's not quite true. So there's so much space in between stars and galaxies, and the way that galaxies interact is they'll start to like do this dance and spiral around each other as they come into their gravitational contact. So them just like colliding together like two cars is kind of not the way that things happen. So what would happen to your local star is probably actually not all that much when two galaxies merge. However, in about 5 billion years, our sun will be close to the end of its lifetime. So things are not looking great for us to still be around at the time of that merger, unless humans are able to do something really awesome and get off of our planet and off of our star. All right. So this now group, so we have our Milky Way galaxy. This is our home where our sun is. This is Andromeda, and you can again see the relative sizes of these galaxies here. So Andromeda is actually bigger than the Milky Way galaxy, but then the other dozen or 2 dozen galaxies in our local galactic group are much smaller. These are what we call dwarf galaxies. Some of them are actually already interacting with the Milky Way. So for example, the Large Magellanic Cloud and the Small Magellanic Cloud, or the LMC and the SMC, are already actively being eaten by our Milky Way galaxy. I think these two are also southern hemisphere, so you have to be in the south to be able to see them. But you can, look at them, and they're starting to get stretched out, and they're actively interacting with our Milky Way galaxy and being eaten by the Milky Way currently, right now. So, but again, from this you can see, here we are in the Milky Way. There are many other galaxies, even just in our very local group here. I'm not sure if we have a distance scale in this image, but so we're beyond our galaxy. We're in a very large portion of space, but in the context, we're still on our local scale in terms of galaxies. So galaxies actually don't like to live alone. If you look out in space and you see one galaxy, chances are that you will see another galaxy nearby rather than seeing empty space. So we call these groups and clusters. So here we are with our local group. Then we also have various other groups and clusters of galaxies that again contain, maybe several dozen or more than that, galaxies, including these dwarf galaxies and these larger galaxies like our own. So here we do have the distance scales. So to get to something like the Virgo cluster, you are 65 million light years away. So here, these distances between different groups of galaxies, again, close to us in our little pocket of the universe, are something on the order of millions of light years. So when you look out in distance in space, you're also looking back in time because it takes light a decent amount of time to travel to you. So light travels 1 light year in a year, fairly intuitively. So for the light that we see coming from the M81 group, that's 11 million light years away, that was light that was created 11 million years ago. So this is another thing that you have to keep in mind when you start thinking about universe scales, is distance and time are both connected. And as you look further out, you're looking further back in time. All right, so galaxies live in groups. These groups then, what do they look like? So now this is something called the Laniakea supercluster, which is how those clusters and groups of galaxies on a larger scale are actually apportioned in the universe. So each one of these white dots here is its own galaxy. So we are somewhere here, and then as you go out, you can start to see the structure of the universe taking shape. So you'll automatically, sorry, does somebody have a question? Okay. So you will automatically see and notice that galaxies are not just uniformly distributed throughout the universe. They have this structure, they have this cluster and grouping. And this is due actually to the fact that our universe contains dark matter. So the 3 components of our universe as a whole are ordinary matter, which is what we're made out of, dark matter, which is something that causes gravity. We don't know exactly precisely what it is made of, but it interacts gravitationally. And we also have dark energy, which is a big mystery that I can talk about if you'd like me to, but let's pass over that for now. So basically, dark matter tells matter where to lie and tells gravity where it's going to be more strong. So for example, if you think about if you were to sit in the center of a trampoline, you and your gravity are acting as the dark matter, causing that trampoline to curve downwards. That's similar to what dark matter does to the universe and does to space-time, causes it to curve downwards and have these potential wells. Then if you were to drop like a series of, I don't know, tennis balls around you on the trampoline, they would all kind of sink and roll towards you until they come to a stop there. That's exactly what dark matter does to ordinary matter in the universe. So it's where you have these pockets of more intense dark matter that you have these galaxy clusters and galaxies forming. So this is why we see this strange pattern of not homogeneous mixed galaxies in structure in the universe, but these pockets and these clusters. All right, so moving on from that, we can get even bigger. So now we are in the Pisces supercluster complex. So again, we're probably somewhere right here in the middle, but we're not even pointing out the local group at this point because that's just merely less than a pixel probably on this picture here. You can see these different superclusters, all given different names, similar to where they are in the night sky. Many of them come from constellations. So amateur astronomers will probably have a much better feeling for where these are in the night sky than I do. But again, you can see this clustering and the structure of the universe taking place, where each one of these white dots is a galaxy, and these galaxies cluster in these groups. Going out even further, so there's a telescope called the Sloan Digital Sky Survey, and it basically looks out into the universe and catalogs all these galaxies that are very, very far away from us. So here's where we are. We're at the center of this beam, and then Sloan, the telescope, has looked out in space across the night sky in these directions here. And so there's this feature called the Sloan Great Wall here, which is, again, each one of these points represents a galaxy. And so this Sloan Great Wall refers to this place in the universe where there just seem to be so many galaxies. It's this wall of galaxies that everywhere you see a galaxy, essentially. So some things I always point out when I talk about Sloan data is you'll notice many galaxies in data here, but nothing here. So sometimes I ask people, do you think there are no galaxies there? And the answer is no, there are galaxies here. Presumably it would look very similar to what you're seeing here, It's just we haven't looked there because you're looking, it's kind of called a pencil beam survey. So you're looking from here straight out into one location and then moving the location and kind of scanning the entire sky as you go. So there are galaxies here. We just haven't seen them yet. Okay.
Zoe?
Yes.
If I may. So what is in the red region?
So the red region, I'm guessing this is a color coding based on distance. So the red ones are basically closer to us. Then you go to yellow or a little bit further away, green, and then blue out here. So we're right here in this center, basically, of where this survey is originating. So the red ones are the closest galaxies to us. So this is where you would see probably these superclusters. Yeah.
Oh, great.
Is that
Thank
your
you.
question? Okay, awesome. Thanks for the question. Anybody else have questions at this point?
What is Sloan? Is it a name of a person?
What is Sloan named after? That's a good question. I would guess it's the name of a person, but I don't know that one for sure.
There's Sloan Foundation.
Sloan Foundation, yeah. So it's called the Sloan Digital Sky Survey. So I perhaps can look that up at the end. Okay, so then, or does anybody else have any other questions before I move on? These have been great questions so far. I really appreciate them. Okay, so then moving out even further. So this is about the furthest out that we have ever seen astronomical observations of. This is called the Hubble Deep Field. So the Hubble is another telescope. It's coming on 30 years old right now. It's out in space, orbiting the Earth every 90 minutes. It gets really beautiful, incredible data. So the Hubble Deep Field, the history behind this is quite interesting. So what they did with the Hubble Deep Field was they took the Hubble Space Telescope and they pointed it at a seemingly empty patch of sky. So no stars, no galaxies that they could see of with any other telescope. They pointed it at that night sky for a span of 30 days or 60 days. I think there was the deep field and the ultra deep field, and they were on the order of like months straight. And mind you, the Hubble Space Telescope, so many astronomers all over the world want to be using this telescope for their observations, for their research. So to take a chunk of a month and say, okay, we're doing a month-long observation of this random piece of night sky, this was controversial. And this was not viewed favorably by everyone because nobody knew if it was going to just turn up absolutely nothing. It turned up the opposite of absolutely nothing. And instead, you can see so many galaxies out there. So what we see when you look at this Hubble Deep Field, you're looking out very far, very deep in distance. You're looking very far back in time. You can see galaxies just clutter all over the sky, litter everywhere. So each one of these points here is a galaxy. There are people who make their living doing research, studying how far away are these galaxies, what can we learn about them, because as you're looking at further away galaxies, you're looking at them as they're forming and as they're becoming galaxies that could eventually lead to present day Milky Way. So this was just incredible to really see how not alone we are in the universe in terms of how many galaxies are out there. So every time I see the Hubble Deep Field, I just feel very, very small. Because if we think about where we started on our Earth in our solar system, which is one star in the Milky Way galaxy, Milky Way is one galaxy in the entire universe, it makes me a little humbled. Okay, so I kind of lied when I said that was the furthest back that we could look was the Hubble Deep Field. So we actually can see something called the cosmic microwave background radiation, which is the earliest radiation that you can see in our universe. And this is the leftovers from the Big Bang, which was the origin of our universe. So the CMB, the cosmic microwave background radiation, is this pattern that you can see here. And it's basically these differences in colors, these inhomogeneities that lead to the differences in dark matter structure, in ordinary matter structure, that eventually allow galaxies, stars, and planets to form. So again, here we're looking at, this is the furthest back we can look. Here's present day. So as you look back in distance and in time, you're seeing this history of the universe play out. So origin of the universe is somewhere back here. Then we have the CMB, the first thing that we can actually see. something called the Dark Ages, and then we get galaxies and stars forming. And this is where that Sloan Digital Sky Survey data, those galaxies that I was showing you before, come out here. So that's about half the history of the universe is in this Sloan data, but then the other half is beyond that. It's before those galaxies started to form. Okay, so now let's take it to the absolute limit here. So the observable universe is something like, here the distance scale is 100 billion-ish light years, or 28 billion parsecs. So astronomers like the unit parsecs. If you're talking to someone in like the general public or talking to your family, they're always like, oh, how many light years away is it? And most astronomers will kind of roll their eyes and go, we don't talk in light years. So just, yeah, that's a little bit of vernacular there between astronomers and other people. But so here we are at the center, Virgo supercluster, one of those big things that contains the Milky Way at the very center. And if you go out 1 billion parsecs, or 30 billion parsecs, you get to the edge of our observable universe. So basically, we can't see beyond that because of the finite speed of light. So the universe has not been around long enough to see any further out than this distance, which is a little bit trippy to think about, kind of blows your mind to understand this. I'm not sure I fully understand when you talk about universe in context like this, but interesting stuff. So then what's beyond our observable universe limit? I mean, we don't really know. Will we ever be able to know? Not really. Is it possible there are multiple universes out there? Sure, there are theories about that. It's interesting to think about. So let me see if I can catch up on some chat questions. So Yanush asks about if our galaxy is special in any way. I don't think our galaxy is particularly special. There are many out there. There is a concept though called the galactic habitable zone, which is the idea of, do you need to be in a certain location in a galaxy in order to have favorable circumstances for life? So for example, if we were in a more dense part of the Milky Way, perhaps having so many supernova or high energy events occurring would limit the possibility for life. Or maybe you have to be in a certain annulus where there are enough rich chemicals to be able to form life. So that's a concept there. But is our galaxy unique? In my opinion, I don't see a reason why it would be particularly unique, but who knows? Then someone else asks, are there infrared telescopes that are able to see further than Hubble, or are we waiting for JWST? So for infrared, JWST is what we are waiting for currently. There have been some infrared surveys in the past. None of them that I know of are super active to this day. JWST is going to be much better than anything that we've had in the past. So fingers crossed that it launches someday and that it gets up in space and unfolds. But we'll see if that ever happens. Okay, and then Kamil says, we are talking about life, civilizations, or nomadic technocultures. So it depends. And that's a really astute distinction to bring up. So there's definitely a difference between life, which, bacterial slime is life, versus civilizations like us. Nomadic technocultures. Yeah, absolutely. So if you hold on for a couple more minutes, I'm going to get into the Drake equation and talk about some of these distinguishing features and some of their differences. Awesome. Thanks for all the questions. Let me pause here and ask if anybody has any verbal questions at this time.
I have a question. I don't know if it's easy to answer, but I remember that during one of the meetings that we had with Dimitar, he mentioned that it might be also important to have a specific generation of stars to produce specific elements that might be important for the formation of living forms afterwards. So what I actually want to ask is actually about this generation of stars which can be formed from the ashes, partly from the ashes of some burnt previous stars. Is it dependent on the position in the galaxy? I mean, do we have regions where we can see second, third generations and some regions where we did not expect them to be formed?
Yeah, that's a great question. So it's less of an issue of space and more of an issue of time. So the first stars to form are going to be very light. So you're going to have them primarily composed of hydrogen and helium. This is because when the universe formed in the Big Bang, it was 75% hydrogen, 25% helium, pretty much nothing else. Then it takes stars forming and using elements in their core to generate energy to make these heavier elements. So once that first generation of stars lives and dies, and they actually had very short lifetimes because they formed very massively, that then you can start to seed the galaxy and seed the universe with these heavier metals. So our sun is what's called a population 1 star, which confusingly population 1 comes after population 2. Astronomers name everything for like what they are currently is like 1, and then everything back in history is higher. So population 2 stars, we can still see those in our galaxy. So these are older, like the older generation of stars, but they're not the first generation of stars. First generation in our galaxy was something called population 3 stars. And none of these still exist to our knowledge. I think people are still hunting for them, see if they might be around, but it's been so long since they formed that they have probably all lived and died and seeded our galaxy with these heavier elements to make things like planets and to make things like life. What are we made of? Carbon, oxygen, nitrogen. You need these sorts of elements to be made by previous generations of stars. So this is why, if you think of the famous quote by Carl Sagan, "We are star stuff." It's true. It's all the elements that you are made of came from stars.
So perhaps a silly question, but is there population 0, or is there any prospect in the future for this to be formed?
Yeah, so you can think about star formation is still occurring today in our galaxy at a slow rate. But yes, so those would be like population 0, I guess. And maybe there's population -1 will come in the future. Yeah, so it's continuing through time. Those are great questions for fall. Thank you.
If I may jump in for a short question, I mean, this is very interesting. Thank you for your feedback. And there is a forever question that that nobody probably knows the answer, but I will ask the question anyway. How unique in terms of elemental composition is really our solar system and our stars in general in our local neighborhood or in our galaxy in general? This was sort of a leading question. That my previous question about the uniqueness of galaxies sort of basically led also to that, because we might if we envision that the differences in elemental composition of various stars and solar systems could actually, the ratios between elements could actually be quite different, then obviously this is going to affect the origin of life and essentially everything around it. Yes, I don't even have to probably go into details regarding that. And as far as I know, people try to even create databases on, to figure out how the elemental compositions of stars and all of this. But this is rather not so thorough research as I would hoped this to be. I mean, I welcome any comments on that, because this is I tried to find this information about that forever, and I've never could. Anyway.
Yeah, it's definitely a great question. Thank you for bringing it up. So you're absolutely right that different stars have different metal contents, and different parts of the galaxy might have these different metal contents, and perhaps that influences the possibility for life. So you know that like we need some amount of heavy metals, of heavier elements to make life, to make a planet like the Earth. So if you're in a very element poor part of the galaxy, yeah, probably, or maybe you shouldn't be looking for life around there. And concepts like this, I think, are so fascinating and so understudied. So like, what it means for origins of life, I think as we approach origins of life, it's reasonable to try to start, I think, with what the Earth is, because we know we have life here. We know it happened here. But does that mean it had to happen this way? I personally don't think so. So,
for example, I will give you just one example and I will shut up forever. Now, the point is, for example, what if you have a star that has 10 times more or 10 times less phosphorus? Yes. Or 100 times more or 100 times less? Yes?
Yeah.
What if?
is so important for life. So
yeah, that's why I brought phosphorus to the forefront of that. But you can have that thought experiments with any element of your choice and basically ask the same question. Yes. But I chose phosphorus for obvious purpose, and I see that Rafa is smiling, and obviously he knows. Yes, and everybody knows. But that's the question, and I don't expect anybody to know the answer. But I wanted to just draw people's attention to actually figuring out even the basics like that. So basically, how different stars and galaxies are with respect to each other, with respect to just elemental composition, might give us an information. For example, is our little Milky Way, or not large Milky Way, sorry, is our large Milky Way really a unique galaxy in our local group or even in the broader universe? And is our star and our solar system unique in any way? Yeah. So that's just a comment. I'm sorry for taking so much time. But...
Oh no, I really enjoyed the discussion and I agree completely, 100%. Yeah. So thank you, Yundish. All right. So continuing on then, so now that we've reached the outer limit of our observable universe, I'm going to, so here's a brief summary. So our universe is, maybe approximately 100 billion galaxies. There are about 250 billion stars in our Milky Way. So maybe, typical large galaxies might have a similar number. Statistically, almost every star has a planet. We know this from the Kepler Space Telescope, which I'll talk about in a bit more detail. So putting all these numbers together, does anyone feel small yet? I definitely feel small when we think about these numbers. So now let's kind of first do a little bit of the history of our universe time-wise, and then I'll kind of work our way back in to the Earth and to what it means for habitability and the possibility of life. And we'll get to the Drake equation eventually, I promise. So we already mentioned the Big Bang, which is the origin of our universe here. And so this graphic is showing you the size of the universe in terms of the radius here, and then also time. So here we are at present day. We're about 13.8 billion years after the Big Bang. And you can see that after the Big Bang, you had this rapid period of growth of the universe called inflation. And then here's the cosmic microwave background radiation, that first pattern of afterglow from the Big Bang. That's really the first thing we can see. This is about 400,000 years after the Big Bang. There was something called the cosmic dark ages before any stars form. But then we get our first stars forming. These will be those population 3 first generation stars about 400 million years ago. And they form from only the hydrogen and helium that was available from the Big Bang and start fusing elements to make heavier elements. So then from the intervening time here, this is when you get galaxies, planets, stars forming. And then you'll notice that as we come closer to present time, the rate of increase of growth of our universe is actually accelerating. So this is the accelerated expansion caused by dark energy, which is fascinating in and of itself, but it essentially says our universe is expanding, and it has been since the Big Bang, but at present day, it is expanding faster than it was in the past. And the reason behind that is given this dark energy, and that's a whole conversation that we can have if you want to. But for now, let's kind of continue to move on. So how do people actually study what happens with the origin of the universe? Well, there's this really fascinating thing called the Illustrious Simulation, where they take different starting conditions and different initial parameters for our universe, and then let gravity and physics happen to be able to see, okay, what kind of structure does the universe have? And you can see in this simulation here, the yellow dots are galaxies, and they actually do start to form these filaments and these clusters that we actually see in the structure of our universe. So you get these voids where there's not much around, you get these clusters where there are galaxies, and you get this filamentous structure that we saw from the Sloan Digital Sky Survey from all those observations of galaxies. So this is how you can kind of try to study how the universe forms and compare it to the data that we actually see. Then down here, I already mentioned that galaxies interact together. Here's an example of 2 interacting galaxies called ARP-87. So you can start to see that stars are being flung out from these galaxies as they come close and interact gravitationally. So this is another thing that's important to keep in mind for habitability, that galaxies are not just their little island universes. They do interact with their surroundings and with other galaxies around them. Now, if we continue to zoom in, so now we're back inside of galaxy, well, how do stars form? Stars form from the collapse of gas and dust clouds in nebula. So these are called the pillars of creation, I believe from the Eagle Nebula. This is another Hubble picture. You'll be able to identify Hubble pictures if they have this weird like section missing from the camera. So I think I've heard the story, not sure if this is true, but that like they had plans to finish these parts of the camera so they could get a nice square image, but then ran out of money. So that's why you have this structure in all your Hubble images. But so stars are being formed at the tips of these pillars here as this gas collapses down under gravity and starts to form these stars. I mentioned this before, but stars burn elements into heavier elements to generate their energy. So for example, our star is undergoing proton fusion. So it's taking hydrogens, slamming them together to create helium. And that is the only thing that our star will be able to do. So more massive stars can fuse together heavier elements, but our star is not massive enough. But if you get to massive stars, they can undergo carbon burning, oxygen burning, all the way down to iron. So this is how you get elements all the way up to the molecular weight of iron forming in our universe. How do you get heavier than that? Well, it's not energetically favorable for stars to fuse those elements, but when stars die in supernova, then you have these massive energetic releases that synthesize your heavier elements like uranium, plutonium, everything that's above iron on the periodic table.
I had a question about that. I mean, Janusz mentioned that what about the star that would have like 100 times more phosphorus? But looking at the diagram you just had in the previous slide, it seems to be kind of not very complicated, not many options for composition of elements, right? So is it even possible that some star would have so significantly larger amount of a certain compound than the others? I don't know.
So I would say it's possible that one star would be much more metal heavy, so like have much more phosphorus, whereas like another star would be very metal poor and only have hydrogen and helium. But getting very different ratios, I think, is slightly more complicated because most of the time when you're forming one set of heavy element, like say phosphorus, you're probably also forming silicon and oxygen and whatever else is around phosphorus on the periodic table. Janusz, would you agree with that?
I would. This is all a game of nuclear synthesis. Yes. So it's essentially, we have to remember that that's exactly what Zoe said, that if you are actually building a star, or you are building it from some sort of nebula, let's call it, then you are not going to enrich with one single element. If you are enriching, then you are automatically enriching with multiple of them and depleting others. There is a database which is, I think, called Hypatia, but maybe I'm actually mistaken in the name of this database. But this is a very interesting database that is in forever preparation. That actually is addressing this question directly, which is basically spectroscopically looking at various elements in the stars, in various population of stars. And you would be surprised because from this very, 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 very limited data set that they have in this Hypatia data set, that might be even a statistical flux. Yes, this is not really something that is very reliable, but let's assume that it is. Yes, let's assume that it is a nice, statistically reliable data set. You actually have a peculiar differences in elemental compositions between the stars. And that's weird. Yes, that's weird because you would essentially assume, okay, it's easy to make oxygen. It's difficult to make phosphorus, yes? And it's also how the nuclear fusion actually happens because, it's mostly you are adding helium and that's great, whatever. But the point is, so yeah, to a degree, you would expect these stars to be actually clones of each other in terms of elemental composition. But the reality is, there are hints that the reality is actually much more complicated, that there are actually quite significant differences. Whether that is true and statistically significant, it remains to be seen because the Hypatia catalog that is currently available simply doesn't allow us to give us this for sure. But if this statistical analysis that they have there is reliable, then there is a possibility that that stars actually differ in elemental composition quite significantly, which is weird, which is really weird.
Yeah, for sure. It will be fascinating to see how that develops in the next few years. So, awesome. All right. So continuing on from stars, why do we care so much about stars? Well, they host planets. That's a very naive way to put this. They're important for other reasons too. But for the purpose of habitability, perhaps the most important thing is that they host planets. So when you look at forming stars, you can often see that they have what's called a protoplanetary disk around them. So they're really beautiful images that have recently been available in the last 10-ish years from telescopes like ALMA, which is located in Chile, which gives you really high resolution and can make really stunning images of these protoplanetary disks. So the idea here is that disks have these structures in them, have these rings and overdensities, and perhaps a ring is the site of a planet actually being formed and carving out that gap in the disk. So here's an artist's conception of what that looks like, where you have these planets in the process of being formed in these protoplanetary disks. Just really awesome stuff. And really, there's a lot of disk literature and work on these protoplanetary disks out there.
Are these natural colors, like violet?
No. Yeah, so these are all going to be artificially colored. ALMA actually sees in the millimeter and submillimeter. So this is all like radio frequency is how you see these.
Thanks.
Yeah. Great question. Okay, so now if we want to look at exoplanets, perhaps the most prolific telescope to date has been the Kepler Space Telescope, where Kepler stared at one little spot in the sky for 3 years. And it was basically monitoring the brightnesses of all the stars in its field of view to see, are there any dips in brightness when a planet passes in front of the star as seen by the telescope that would indicate that a planet exists around that star. And from those continuous observations, you can get, if there's a planet there, you can determine the size of the planet relative to the star. You can determine the period of the planet and then get a measure of how far away from the star it is. So I don't think I have the animation working on the slide, but if you go to this Kepler orrery, you can see basically a little GIF of all of these planets circling with their real-time periods, and well, not real time, but just relative to the star. And you can see basically from looking at this that there are all types of planets. They're not all uniform in what they look like in all these different systems. You can get massive planets, you can get little planets, you can get multiple planet systems, planets orbiting really close to their stars, planets orbiting further away from their stars. But so what Kepler taught us really was that planets are ubiquitous. They're out there in plentiful numbers, which was really important because before the Kepler Space Telescope, people did not know if every star had a planet, if every 10 stars had a planet, if every 1,000 stars had a planet. So we did not know how common planets were around stars until Kepler showed us, hey, they're everywhere. So moving on to a specific planet. So Proxima Centauri B was an exoplanet discovered in 2016. This was really cool and really fascinating because Proxima Centauri B is the closest star to our sun. It's part of the Alpha Centauri system, which is actually a triple star system, where you have this binary of Alpha Centauri. So 2 stars circling each other, and then you also have a triple, which is this Proxima Centauri orbiting further away. Proxima Centauri is an M dwarf, so one of those small red stars, and it has an exoplanet orbiting it, and it was discovered with something called the radial velocity measurement. So you can see basically the star wobbling, which indicates the presence of a planet around it tugging on that star. And so this exoplanet is potentially within what we call the habitable zone of the star. So that was very exciting. First of all, to realize that our closest stellar neighbor has an exoplanet, and second, to realize that this exoplanet might be rocky and might be within the habitable zone. So I mentioned habitable zone. What is the habitable zone? So this is the area around a star where the possibility for liquid water to exist on the surface of a planet is there. So the habitable zone is going to depend on the type of star. So like here's our sun, one of those bright yellow stars. Here are those M dwarfs, one of those smaller like Proxima Centauri stars. And then the location of the habitable zone, this is distance from the star. It's in a logarithmic scale, so just note that one. So planets have to be closer to dimmer stars in order to have liquid water on their surface. further away. So a nicer version of habitable zone figure is something like this one. So again, we have stellar type here, and then we have the starlight and the distance located here on this axis. So habitable zones are hard to get right. There are many different parameters that go into these calculations. So people sometimes break them up into the optimistic habitable zone and the conservative habitable zone. So for our star, both the Earth and Mars, you can see, are within the conservative habitable zone. And then here are some of the other habitable zone planets that we have potentially found so far. So here's Proxima Centauri B. And then another system that got a lot of press in 2018, I think, was the TRAPPIST system, where there's basically a star the size of Jupiter. It's really faint, it's really small, has like 7 planets orbiting it very close, and like 4 or 5 of them are potentially within the habitable zone. So this is a way to consider what planets out there could potentially host life, according to this liquid water habitability zone. But what about habitability beyond the habitable zone itself? So does liquid water exist only in our solar system within the habitable zone? No. So the story is more complicated than this. And this comes into play with, say, the moons of the giant planets, like some of the moons of Jupiter and Saturn. So here's an image of plumes of liquid water erupting from the surface of Enceladus, which is a moon of Saturn. So Enceladus, it has an icy shell over it, then it has some sort of geothermal activity that then causes these plumes of liquid water to be ejected from the surface and out into space. Here's Europa, which is a moon of Jupiter, which has, again, an icy shell covering it, but then a deep, salty ocean of liquid water within it. So many of the moons of the large gas giant planets are interesting because they could and do have liquid water. But then there's also the potential, speaking of, does all life need to have liquid water to exist? Maybe, maybe not. So are there other solvents that could be useful for life and for habitability? Maybe. So the intriguing moon here that we always bring up is Titan, which is a moon of Saturn that has liquid lakes of liquid ethane and methane. And these lakes actually ebb and flow over time. You can see geological features appear and disappear as these lakes grow and evaporate. So there's going to be a mission to Titan to go fly around in a little helicopter, Titan Dragonfly, that will be happening in the next 10-ish years, 10, 20 years, something like that. So yes, I agree. Alternative solvents do rule. Okay, so that's just something to keep in mind. But now getting to the fun part here. So the Drake equation, I don't know if you've heard of this before. This is a way to estimate the number of technologically advanced civilizations in our Milky Way galaxy. This is a combination of factors. So it's a probabilistic equation. It's not like solving Kepler's equation or solving the Schrodinger equation where you get an answer out. So let's go through some of these factors. First thing we have here is R star, which is the rate of star formation in our galaxy. Then we multiply that rate of star formation by the fraction of those stars that have planetary systems. Then we take that fraction of stars with planetary systems multiplied by NE, the number of planets in each solar system with an environment that could be suitable for life. So if you think both Earth and Mars are like that in our solar system, then NE would be 2. Then you take that and you multiply by the fraction of suitable planets which actually develop life. So if Mars never developed life and never will develop life, but you think it could have developed life, then your FL would be 0.5. Sorry, I went too fast. And then you take those fraction of planets that actually developed life, multiply by Fi, which is the fraction of those planets that develop intelligent life. So here, are humans intelligent? It's debatable, right? That's a joke. But like, are dolphins intelligent? Are octopi intelligent? I would say yes. So the Earth did develop intelligent life. But then the difference between dolphins versus humans becomes apparent in this next factor, which is FC, which is the fraction of civilizations that develop a technological signal. So humans have done this, dolphins have not. And then the last thing you multiply by is L, which is the longevity of that technological signature. So on Earth, the longevity so far has been like between 50 and 70-ish, 100-ish years that we have been releasing technological signals to space that could feasibly be detected by other aliens. And so the overall number that you get when you multiply all these together is the number of technologically advanced civilizations in the Milky Way galaxy. So this is not number of life in the Milky Way galaxy. This is technological civilizations that you could detect currently. All right, so now here's the part where I'm going to ask for some input from you guys, if you don't mind. So let's just go down the best guess column. So I gave you our star because that's kind of finicky from an astronomer's point of view. Basically, we get about 1 star being formed per year in the Milky Way galaxy. Can I get anybody want to give me a guess for FP, which is the fraction of stars with planetary systems?
Almost 100%.
Almost 100%. Okay, so I'm going to have to exit here so that I can actually type in, get my calculation to work. So I agree with that. Let's just go with 1 there. Okay, anybody have a guess for any? This is the number of suitable planets per solar system for life.
My guess is 1.
Sometimes 2. It actually really depends. But I don't know, when we think about the TRAPPIST-1 and our solar system, maybe it's I don't know, the upper bound.
Okay, we can do multiple columns too if people have different opinions. So,
yeah, let's try 2.
Let's be conservative and assume that every planetary system has 1.
Okay, good.
Okay, and then let's go with FL. So now this is the fraction of those planets suitable for life that actually develop life.
Like 1 for 3, like
one out of 3. Okay.
Yeah.
I don't know if it's like that. Okay.
The question is to our resident experts on the origin of life, I guess. You guys should have figured that out a long time ago.
It's more
working.
harder than you think. Yeah.
It was lockdown. We couldn't work.
Yeah.
Excuses everywhere.
All right. So now what about for FI, which is the fraction of planets that have life that develop intelligent life? What do we think about that one?
Extremely small.
Extremely low.
Okay. Give me a number, like 1 in 100 or 1 in 1,000?
1 in a trillion.
In a billion, right, or a trillion.
Really?
Oh.
Yeah,
I once opened the best bottle of whiskey that I had, and I actually did these calculations in more sort of.
I think it will be higher.
And really, I mean, I think that we are alone in our local group.
Question, how do we define life?
Yeah.
Do we use the life with an I or the life with an Y?
I mean, we are on the level of intelligence now.
Yeah.
Yeah.
I am the counterintelligence.
No, it's very rare because it happened. I mean, it's a discussion in its own, I guess.
Yeah.
But for example, on Earth, we have more than 1 intelligent species and few of others who are extinct now, but they were probably intelligent to some extent.
But there is a question.
It was all quite recent.
Yeah.
Most of the
and
time.
this is all within the same or very similar evolutionary branches. Yes.
Actually,
if you consider insects, it's not so similar.
Well, it depends how you define where are the borders of the intelligence, I would say. But yeah, I guess okay, intelligence itself and the technological intelligence are 2 different things.
Yeah,
absolutely. Yeah. So I've put in some numbers here, arranged. So feel free to agree or disagree, or let me know if you have issues with these. But we can get our low estimate, high estimate, best guess. So the next one that I want your opinions on are this L. So that's how long does a technological civilization stay technological? So anybody have a low estimate, high estimate, or best guess?
It could be thousands of years, because the point is, are we talking about the period when they become detectable? So if you think about humankind, the problem is that when we became detectable, we also started destroying our planet. So the question is for how much longer we will, continue to be detectable and exist here. I don't know, is it thousands or tens of thousands of years?
There's also the idea of what is a civilization. How do we define it? Because, well, from my point of view, one of my favorite tropes in science fiction and futurology were macro life. the Dandridge Coyle's idea of mobile utopias, where they were both minor hunter-gatherers, but also a closed ecosystem and a civilization at the same point. So they weren't static, they were mobile, where civilizations are mostly stationary.
Yes.
Yeah.
Yeah, absolutely.
I'm optimistic. I think when one is born, it's going to last forever.
Yeah. Okay. So, yeah, so I put for high estimate like 10,000, best guess, I put 300. I guess I'm feeling, I don't know if that's optimistic today, and low estimate would be 10. You can agree, disagree, you can do this calculation on your own if you wish. Then the other thing that we need to draw the contradiction between this intelligent technological life and simple life is the life of, or the longevity of a simple civilization. So I think I have my zeros wrong, but simple life has existed on Earth for like 3.5 billion years-ish. So 1, 2, 3, 4, 5, 6, 7, 8, 9.
Oh yeah. Once it originates, it is almost impossible to eradicate.
Exactly, yes. Yeah. So if we put these numbers in here, so for our technological civilizations, in our high estimate, if we're optimistic, like I think Rafal seemed to be the optimist here, get hundreds of technological civilizations in our Milky Way galaxy. If you're Yanush, you know, it's 1 in a trillion, or 1 in however many zeros that is. If we're doing our best guess, it's maybe 1 in 1,000, 1 in 100. Yeah, so on that order in our Milky Way galaxy. But the story now changes if you consider only simple life. So simple life lives a lot longer. You don't have to go through these tricky elements here like intelligence and communication. So there you would get, what is that, billions of simple life in our Milky Way galaxy. So let me go back to make this a big thing. So that's kind of the thought experiment and the estimate you can do with the Drake equation here. So let's see, I did have a bit more going on to talk about the Fermi Paradox, but I know we're at the hour, so I want to be respectful of that and ask, should I stop here? Or if you would like me to continue, I'm happy to go on, but I don't want to keep you guys. I know it's late where most of you are.
I'd be happy to hear more. If anyone needs to leave, we're recording here. It depends on your time, if you have it. Yeah.
I'm happy to do it if you guys are, but I won't be offended if you leave. Please feel free to leave.
If anyone leaves, gonna be able to see the recording.
Okay, awesome, wonderful. Thank you so much. We're having great discussions too, so I so appreciate that and really value the feedback and the interaction. It's a lot of fun. All right, so that was our Drake equation, which basically, let me go back to the previous slide. So this says that, hey, you know, maybe if we're being optimists or we're being best guess and not super pessimistic, maybe there is actually a decent amount of life out there. And reminder, this is only for our own Milky Way galaxy, and this is only kind of at present time. So what about in the past? So this is essentially the setup for the Fermi Paradox, which is that we had the Big Bang 13.8 billion years ago. Suppose that there's some planet X born 8 billion years ago, and Earth was born 4.5 billion years ago. So if planet X, at the time of planet X forming, again, if there was that, you know, maybe 1 in 100, 1 in 1,000 chance of getting to a technological civilization, well, 3 billion years is a long time. So maybe you had this happen multiple times between the Big Bang and between now. And maybe if those civilizations were able to advance throughout the galaxy, shouldn't we see them by now? So where are all the aliens is essentially the Fermi Paradox. So there are many ways to combat the Fermi Paradox and to try to rectify this. So first, let's do a little thought experiment on the numbers illustrating the Fermi Paradox. So if math is not your thing, feel free to tune out. I won't make you do math, but I will put math on the slides here. So this is a problem that I would make like my undergraduate students do and torture them with that, but I won't do that to you. All right, so for our Milky Way contains an estimated 300 billion stars. Let's approximate the Milky Way as a disk with a radius of 30,000 PC is parsecs and a height of 300 parsecs. So now these are the conversions between parsecs to AU and AU to something more tangible like kilometers. So we can use this to ask what the average stellar density is in the Milky Way. So we can calculate the volume of this disk with this size and then take the number of stars and divide the number of stars by the volume, and you get something like 0.35 stars per cubic parsec. That might not mean too much because a cubic parsec doesn't mean much to me. Basically, it's a huge amount of space because a parsec is huge as well. So now let's convert this into something like stars per cubic kilometer. And then we'll use that average stellar density to determine the average distance between the stars to get something a little bit more tangible. So you take that stellar density and it actually turns into 1.2 times 10 to the minus 41 stars per kilometer cubed. So not many stars in each cubic kilometer. That makes sense because a cubic kilometer is fairly small on an astronomical scale. So we can estimate the average distance between stars from the stellar density by taking that stellar density to the negative 1/3 power. So take the negative cube root. Okay, and then we turn this into a value in kilometers and you get 4.36 times 10 to the 13 kilometers. So this actually turns into, sorry, what? Okay, awesome. So our nearest stellar neighbor, the Proxima Centauri B, is about 4.2 light years away, which is 4 times 10 to the 13 kilometers. So we're actually pretty close. We're within the same order of magnitude, very close based on our average stellar density here. Okay, so now let's talk about spacecraft and speeds. So the Voyager spacecraft was launched in 1977. It's traveling at roughly 61,000 kilometers per hour. So we can use this to calculate how far away Voyager is from Earth at the present time. So we can do this by saying distance is velocity times time. So we take our time between now and take the distance and convert this, and you get that it's about 154 AU away. And every time I think about this, like when we're talking about the scale of the universe, 150 AU doesn't mean like much, or might not sound like much, but this is a human-made thing that is now beyond our solar system, which I just think that that's a really fun thing to remember, that humans have now sent something past the outer limits of our solar system. It's 150 AU away, roughly. So now if something is traveling at Voyager's speed, how long would it take for that spacecraft to reach the nearest star, assuming that it was located the average distance away? So again, we can take our distance between the average stars, take that velocity, convert it into a time, and you get 74,000 years. So 74,000 years, Voyager would be as far away as the nearest star. So you'd have to wait a very long time for that to happen, essentially. But if in the future, space travel is much faster, let's say maybe you can get up to 10% the speed of light, or about 10 to the 8 kilometers per hour, how long then would it take to get to the nearest star? Do the same calculation, take that distance, use the speed, and then your time becomes something more like 45 years. So within 45 years, within a human lifetime, you could potentially get to the nearest star if you can go 10% the speed of light. So you might say, is 10% the speed of light reasonable, feasible? So I think I mentioned briefly a project called Breakthrough Starshot when we were talking about Proxima Centauri. This is actually a project to send nanosatellites to Proxima Centauri and to Proxima Centauri B. And their plan is to go at a velocity of 20% the speed of light. Now, this is a nanosatellite, so it's very small, and they're going to try to use high-powered lasers to accelerate like star sails to get to 20% the speed of light. But it's not unreasonable to have something moving at that speed, perhaps. Whether or not you can get like a big spacecraft the size of Voyager or a human spacecraft going that fast, that's a different problem. That's probably much further away for us to get there. All right, so then suppose that we now have a civilization that goes about colonizing nearby stars in space with spacecraft capable of traveling 10% the speed of light. We're going to assume that all stars are the average distance apart and assume that it takes 1,000 years to colonize a new planet around a new star to the point that it can be used as a node for the next colonization. So then how long would it take to colonize the 5 stars using each previous colony as the base for the next one? So we have our average stars of distance away. And we have our 45 years to get from one star to the next, and our 1,000 years to colonize. So you get something like 5,000 years, 5,200, want to be more precise for that. So then, now let's assume that there are equally spaced stars across the entire galaxy, and that the radius of the Milky Way extends for about 2.1 times 10 to the 4 stars, so 21,000 stars to get from the center to the edge. So then how long, given these same parameters, would it take to colonize the entire radius of the galaxy, given the same assumptions that we previously used? So from that, you can do the calculation. you get something like 22 million years. So 22 million years to a human sounds like a lot, but the age of the solar system is 4,500 million years, 4.5 billion years. The age of the galaxy is 13.5 billion years. So then you can ask the question, well, where are all the aliens? Because if even one of them became technologically advanced enough to do this colonization, they should have been able to start colonizing the galaxy and make their way across the entire galaxy in a fraction of the time of the history between now and then. So this essentially is the Fermi Paradox. Where are the aliens? They should be visible by now. So there are some potential solutions to the Fermi Paradox. Some range from plausible and maybe boring or a little sad to implausible and fascinating. So some possibilities are just that planets are fragile and life is fragile. So if you have an asteroid that comes and hits a planet, like happened with our dinosaurs, you can get mass extinctions. You could get episodes of lots of volcanism that could eradicate life. Maybe that stops a lot of life from developing to the point where it can be technologically advanced enough to do this colonization. There's something else called the rare earth hypothesis, which is just the fact that maybe complex life is really, really uncommon. Maybe here on Earth, we were extremely, extremely lucky and fortunate to get to the point where we have intelligent and technological life. And maybe there are lots of roadblocks to get there. And we saw that come up in our Drake equation thought experiment there.
What do you think about the argument that Earth is not very young? It's like 1/3 of the age of the whole universe, right? If we calculate, yeah. So
yeah,
maybe, and life, like intelligent life, just started here. So maybe it just takes a lot of time and we're first, I don't know.
Yeah, and maybe like if you have one of these mass extinction events occur at any point before you get to intelligent life, maybe you erase that possibility. You have to start over again, essentially, which would be sad,
but a very massive extinction, like a gamma ray burst, reverting everybody to a single cell organisms on the bottom of an ocean or something like that,
Yeah.
Because we have to remember, I mean, this is just one simple comment, which I always have this with problems with this various explanations, is that I think that it is inherently the Fermi paradox is evolutionary, and it's not catastrophical or anything. If you think about it, I mean, the basic building block of a vertebrate that could be potentially intelligent is many millions years old, many tens of millions years old. Yes, and in principle, you could start selecting for intelligence much earlier than you did on Earth. So there probably is some sort of the number of conditions that allow this selection to even happen is actually quite limited, and I think that this is the problem. And then specifically to test selection towards select technological intelligence is another one. I have a lot of materials on that. At some point I have to write an article about that as well. But anyway, I would welcome your comments on that as well, of course.
Yeah, absolutely. I agree. I would eagerly look forward to reading your article on that. Okay, so other potential solutions to the Fermi Paradox. This is when they start to get a little bit wackier, but not even as wacky as they'll go, that I'll talk about. So maybe aliens are out there and maybe they've already been here. If you think about Area 51 in the US, there's big government conspiracy theory. Maybe the aliens were there and, government isn't telling us about that. Maybe we're not listening correctly. So we're looking mainly for radio signals to hear because we think that that's how aliens would detect us. Maybe they do things very differently. Maybe they're technologically different from us, so we're not listening correctly. Maybe for all the Star Trek fans out there, I feel ya. I'm also a big Trekkie. So maybe civilizations like just doom themselves, and this is the doomsday machine where two warring planets made a doomsday thing that ate planets and just went around the galaxy roaming and killing things. So maybe civilizations do it to themselves. Let's see. Then we can get even more so crazy out there. There's the idea that perhaps we are in a simulation and everything that we see in space is just a simulation that aliens wanted to paste up there for us. And we aren't seeing them because they're controlling the simulation and making it so that they are invisible to us. maybe we're like little zoo specimens where aliens put us here and seeded life on different planets and wanted to see how their experiments grew. And for that, they're not letting us see them. So this can be kind of like the prime directive in Star Trek. You're not allowed to interfere with developing civilizations, maybe. Okay, so those were some of the, you can see we went from more plausible solutions to the Fermi Paradox, like natural disasters, to perhaps a little bit more out there, to totally out there, but still fun to think about, in my opinion. So which ones are more likely? You can come up with your own opinion, or even if you think the Fermi Paradox is a paradox or not, just to put some thoughts in your head there. So just kind of to sum up, this is a picture of Earth from one of our spacecraft that turn around and look back on Earth. This is the pale blue dot. So we are just a pale blue dot among many others. So if you think back to this Hubble deep field, the deepest structures of the universe that we can see, where we see galaxies everywhere, stars everywhere, planets are everywhere. So yeah, are we alone out there? My gut feeling is no. Are we the only intelligent life out there? Maybe that's more likely, but who knows for sure. So with that, I would just like to, again, thank you for inviting me. Thank you for all the comments and thoughts and discussions. That was really fun and really valuable. And I always end every talk I give with a picture of my pony, Peter. He says hello.
So cute.
Yes. All right, and I think that about ends it for what I had planned to talk about, but if anyone has questions or anything further to discuss, I would be happy to, but I also don't want to keep anyone longer than they would like to, so feel free. I won't be offended if you leave.
Yeah, I want to thank you because this is our first English speaking lectures, and it was wonderful. Like, the subject was just perfect. I think we all enjoyed it a lot, so thanks. Thanks a lot.
I'm very glad. I was very intimidated to be your first English speaking lecture when Paul told me, so I hope it was okay.
It was really fantastic, Zoe. Thank you.
Awesome.
Excellent. Do we have any questions?
I would ask one question. Are we looking for a non-water-based life?
So are we actively looking for it? I think
yes, non-water. Yeah, did I understand it well? Like something based not on water?
Yeah.
Yes, like based on, I don't know, ammonia or silicon.
My former lab, there was one person working in the lab who was working on alternative genetic polymers. So stuff that is not like DNA, but still had properties to be able to encode information and transmit information. And his molecules would not work in water, but would work in something like more of an organic solvent. So I think people are starting to foray into that in the laboratory aspect, just like how might this stuff work? But in terms of, is anybody looking for that? I would say the closest that we're getting to is something like Dragonfly, which is going to go to Titan and explore the chemistry. Whether or not that's a life-finding mission, I think it's more just a geochemistry of the moon. So yeah, I think we have a ways to go, but I think that that is a vastly understudied portion of astrobiology, and I would be super, super interested in the field really moving in that direction.
Thank you, and thank you for your lecture.
I mean, this is I love this topic. Like, I mean, this is my thing. Like, it's so out there that I love it. Like, I like this a lot. Absolutely.
Yeah. And it's so hard that, like, obviously the easiest thing to do is assume that life is like us. It's made out of carbon and uses water.
I don't like to assume that life is like us all the time. I don't like that. But I know that we have a difficulty figuring out how life originated in water. So now try to translate what we know about that to something completely different. I mean, it's an insane topic.
Yeah.
It's an insane topic.
Zoe, go ahead, Rafa. Okay, Zoe, I have a question on the Bracewell probes and the so-called von Neumann probes. What is your take on the Kepler's argument that if we don't find self-replicating probes terraforming and inseminating life everywhere in the galaxy, that this means that, intelligent life doesn't exist? And will it be that, even our, well, we call astronauts the envoys of mankind in international space law, but will it be that all the envoys we would actually have, ours or the extraterrestrial ones, would be machines?
That's a really fascinating thing too, is the idea, what if you can transmit information purely through machines? Thank you for bringing that up. So I'm not an expert in some of the things that you mentioned. I would have to familiarize myself with that. But I think it's very interesting concept that, you know, maybe we would see these technological signatures that could operate without humans or without life behind them. But if you don't see them, does it mean that there's no intelligent life in there? I would lean towards no, because there are many issues and problems with space travel as well. So one that I didn't mention for the Fermi Paradox is that it's really expensive to get things into space, right? Like to overcome the gravity of a planet to get up there. So it's possible that you would have an intelligent civilization out there that maybe because of their intelligence, they would focus on sustaining their planet instead of expanding to other planets, something like that. So I think there's a lot, maybe you can get into like the psychology of aliens or extraterrestrial intelligence, what it would be like. There's a lot we don't know about biochemistry of other life, let alone intelligence and psychology of other life. So I don't know if that in any way answered your question, but that's the tangent that I went down.
Thank you.
Zoe, if I may follow a bit on the whole idea of different solvents, which Janusz likes so much. I mean, I remember once having a nice discussion with Matt Pauner, our other colleague interested in prebiotic chemistry, about it, and we were thinking together that probably polar solvent could still do good work in promoting even some kind of unknown biochemistry to us. I know Janusz has many other ideas, but staying, you know, on the conservative side, let's think about the polar solvent. How about ammonia? Do you know, is it possible under planetary conditions to have oceans of ammonia? I mean, probably not in the solar system, but in some other places. Has anyone considered it?
Yeah, so ammonia is definitely interesting because it has that polarity to it. It can also hydrogen bond, similar to water. So that's kind of one of the go-to solvents sometimes people think about. So ammonia will be a liquid at much colder temperatures. So like on Triton or on some of the moons of the outer planets, you can have ammonia ices and ammonia liquid mixtures as well. So yeah, if you go beyond the habitable zone to like the ammonia habitable zone, that's further out from the star. Yeah, and maybe you can get some interesting chemistry going on there. I think that's a great idea.
Can I comment on this? I have to comment on this. I mean, I have to comment. So the problem with ammonia, I love ammonia as an alternative solvent, but you know what's the problem with it? It's not that it cannot build biochemistry, like some weird biochemistry, or support biochemistry, like, because it's, apart from water, it's actually the most attractive one. Yes, but the problem is that it's very miscible with water. Yes, so whenever you would actually have to have very weird conditions in which ammonia and water are somehow separated, like maybe some range of temperatures when actually ammonia is liquid and water is just like ice or basically like rocks or something like that. So that's the first thing. And the other problem with ammonia is that is actually quite, it's for example, very photochemically reactive. Yes, so much more photochemically reactive than water. Yes, so that's a problem, because if you are a planet, when you have like in this ammonia habitable zone, you effectively do not want to react away your solvent.
Yeah.
Yes, and the problem is that you know, when you photochemically react with water with photochemically react water, then effectively you also can remake it photochemically as well. So there is a cycle of not losing it permanently, but unfortunately photochemically you could lose this ammonia and become nitrogen N2, and then that's it. You have a sink for your wonderful ammonia that you cannot really recycle again. And that's the problem. So that's why if ammonia is ever a solvent, then it automatically has to be farther away, maybe underneath the surface of Pluto, when you could have in principle like an ammonia water mixture as a solvent for something interesting that happens. But this is just my short. I could talk about it for hours, of course. Thank you.
Yeah, I agree completely. It's very important to think about. Yeah.
Do we have any other questions?
Well, the question also is, again, what do we define as a civilization? Because from an anthropological standpoint, we have many tool-using species. Not many of them are considered civilized. And well, there is even the concept, okay, we had well, very developed cultures in even human history that weren't civilized in the sense that they didn't build centralized urbanized areas or very much hierarchical structures. So that is also the idea, for example, in the School of Meta Law, which is a part of international space law, although today it's more like ethics and philosophy, or even let's say history of space law, because not many people are still interested in it. But it was developed in the 50s and 60s, before we knew that, well, Venus is in jungles and Mars doesn't have Martians on it. So anyway, there was the school of thought that that was interested in can we, well, not can, but what are our legal relations with extraterrestrials? And the question also was, okay, so what is an intelligent and civilized extraterrestrial? Do we see, let's say, hive-minded animals like insects as civilized? For example, do we have, if they have like those structures like hives or I know, let's say just ant hives, bee hives, and so on. They are very complex. They create structures, but well, they don't have a culture. There is a difficulty with communicating with them. So this is also an idea that was in the book by Carl Schroeder, The Permanence, where there were one of the aliens that they encountered were actually remnant, well, let's say, very highly sophisticated robots that could only do certain tasks and conserve the remains of a megastructure. So the same way as in well, Stephen Baxter's Return to Titan, when they actually didn't find intelligent life, but they found robots. So well, robots that don't come out, don't pop out out of themselves through evolution. They have to be created. So yeah.
The Cloud.
Yeah, the Cloud from the Invincible by the Stanisław family. Yes, we are Polish, and you have to remind everybody else that we had a writer called Stanisław Lem. But anyway, yeah, there are different approaches, like even with cetaceans or octopi. So that is the question, because we are still looking for, well, rubber forehead aliens from Star Trek. We are looking for other humans with similar structures of, well, with similar technology. Because, well, of course, we have the basis for it, because even orangutans can spear hunt with a spear hunt for fish.
Yeah.
That's my take.
Yeah, fascinating questions that you bring up. I agree.
Yeah, I mean, you can, if I may, one last question or something to discuss maybe at some other point. The question is, for example, could you actually have a technological civilization without fire? Yes, without a possibility for generating an explosive reactions like that, and I mean, and that's a legitimate question. Can you actually develop technology properly that you could actually go to space eventually and something like that? You know, I mean, maybe those things are connected. Like we have to first have oxygen atmosphere to then develop the complex life, and then basically, you know, oh yeah, automatically you have the ability potentially to make the to achieve technological civilization. But that's also something to have in mind. Yes, what if your environment doesn't allow you to have chemistry that can lead you to actual technological civilization? Yes, so that you cannot oxidize something vigorously in very easily, you know, in an environment of your planet. Then what? You are stuck forever. Yes.
Harnessing fire was incredibly important if we think about it, that for the first time, something made of water and lipids, that's what we are, in proteins, of course, started using energy that wasn't proportional to the strength they can generate with their own muscles, right? So just one person can burn down the whole wood or the whole forest and just collect things. So it is impressive what we can do, and that's connected to the chemistry of a planet. So pretty interesting thought, Janusz, thanks.
And I don't think, and this is a question to other more chemically oriented people, but I don't think that there is any planetary common oxidizer that we could substitute easily.
Yeah, so we have to have life to generate enough oxygen to be able to start having technology, right?
Because can we find any other type of substitute for oxygen as an oxidizer for this type of reactivity that we could, in principle, have an analog of? Not exactly, you know, having a fireplace somewhere with some other, but an analog of that would lead to the technological civilization. And I don't know, to be honest. I don't know. I don't want to say no, we cannot or whatever, but I don't know. Just something to think about, you know.
Okay, guys, thank you so much. Thank you for a very nice discussion, and then some really great ideas. I really loved the part about solvents.
If you have any friends that you think would like to have a seminar for us, please think about us and let us know. And shout out to everyone. Like we don't have a next speaker invited. Janusz, you send me an email. You might have a problem with organizing another speaker for next month.
So in my September might be actually quite I might travel a lot in September, so it might very well be that I will miss the September meeting. I don't know yet, but I wanted to give you an information about it early enough so we can in principle find a substitute.
So I'm going to send an email the dates, and please suggest speakers to invite. Thanks.
Thanks. And thank you, Zoe, once again for your wonderful presentation and very stimulating discussions.
Thank you all for having me. Thank you for the wonderful questions and discussions. I really enjoyed it.
Thank you. Good night for some. Good day for others.
Yeah,
good night
good
and
day,
thank
Zoe
you.
and Tomek.
Bye. Bye-bye to all.
Bye.
Bye.